Hi, long time no see. It's been like months I uploaded, but this video is going to be so long as this is quite a long paper by pathway and I will explain every fucking details, every figure, every equation in details so even a 15-year can also understand this. But no worries, if you have short of time you can see the just last 5 minutes where I explain the whole paper in shortest way possible. But if you want to learn wholly deeply, you can see the detailed one. Hope you like it and let's get started. So, in this paper, the authors are trying to solve a very big problem in AI: how to make models reason over long periods of time like a human brain does. So, right now, most models like transformers are powerful, but they don't naturally generalize reasoning over long sequences. So, the authors introduces a new architecture called BDH, Dragon Hatchling, which is built like a neuron network of neurons connected in a graph, similar to how the brain works. You can relate this like a social network. Each person is a neuron that talks to a nearby people, but together they form a powerful system. This model uses concepts like attention, state space models, and synaptic plasticity. That's Hebbian learning, meaning it can learn while thinking, not just during training. Interestingly, even though it is a brain inspired, it still matches transformer performance like GPT-2, which is huge. And the key idea is that what we call attention in AI can actually be understood as local interaction between neurons, which they call the equations of reasoning. This can be understood like this: instead of one big centralized systems, many small units interact collectively and they produce some intelligent behavior, just like neurons in your brain, helping you understand your language right now. So, in this introductions, the authors are just explaining a core limitations of current AI models. They struggle with long reasoning over time, and today we expect language models to handle complex tasks for a single prompt, sometimes equivalent to weeks of human thinking. But models like transformers don't truly generalize their reasoning beyond what they have seen during the training. You can relate this like a student who can solve problem they have practiced but fails when the question becomes longer and slightly different. Technically, even though transformers are Turing complete, meaning they can complete anything in theory, they don't efficiently mimic how the human brain actually reasons, which is a massive graph based distributed systems with billions of neurons and connections. Like, instead of one centralized systems doing all the calculation, the brain works like a huge networks where each neurons only talks locally but together creates intelligence. The problem is current models use tensor operations while the brain uses graph based interactions. And this structural mismatch makes it hard to connect AI with real brain function. So, the main goal of the paper is to bridge this gap and find a direct link between transformers and brain lens systems. So, now the authors explain why we need a model like BDH. AI and neuroscience have always tried to solve the same problem, that's understanding intelligence, but even after advances like neural networks, backpropagations, deep learning, and attention, we still don't understand the two key things. First, how small neuron level interactions, that's micro level in the brain, lead to complex reasonings, that's macro level. And second, how current AI models actually relate to the brain. You can relate this like trying to understand how individual people in a city create large scale traffic patterns. Like, it's hard to connect local behavior to global outcomes. Similarly, the brain works as a distributed graph systems with local interactions, while transformer works with dense tensors and centralized computations, so there's a mismatch. This can be understood like one system is like a network of friends, passing messages locally, while the other is like a centralized server processing everything at once. Because of this gap, we can't predict how AI behaves over long time periods, which become dangerous, like the paperclip factory. which is a problem where AI optimizes the wrong goal endlessly. So the author proposes a goal: build scale free models whose behavior remains stable as they grow in size and time, similar to natural systems, and move towards something called axiomatic AI, where we understand both the small level rules and the large scale behavior. Now, the authors are explaining the core intuition behind the BDH, which combines logical reasonings, that's modus ponens, where might have heard in this mathematics you have, with learning, which is Hebbian learning. Modus ponens is like a basic logic rule. If fact I is true and I implies J, then J is also true. You get this point? You might have heard this on this terms in maths. So in the model, this is written as xi sigma ij implies a of ij, meaning the belief in I spreads to j through a connection sigma ij. You can relate this as like if you know it's raining and rain implies wet roads, then you can conclude roads are wet. Now let's come to Hebbian learning. Neurons that fire together wire together. Meaning, if two facts activate together, the connection between them becomes stronger. It can be written as yixj implies sigma ij. Like if you repeatedly see rain and wet roads together, your brain strengthens that connection. Combining both the system not only reasons but also updates its rules while reasoning. So next time it reaches conclusions faster. They also introduces the idea of fixed rules, that's model weights, and dynamic rules, that's fast weight sigma, where sigma acts like short-term memory. You can think of it like a student who has textbook knowledge, that's the fixed rules, but also learns from solving new problems, that's dynamic rules. Finally, by making these connections sparse, the whole systems became a graph of neurons and synapses, making it closer to how the brain works. Now, the authors are clearly state that what they contribute with BDH. The main idea is that they model a language model as a distributed systems of n neurons, that's particles, connected in a graph where both parameters and state lives on edges, that's synapses, and reasoning happens through local interaction, not global matrix operations. Like imagine a network of n students that are neurons, each only talking to nearby friends but together solving a complex problem. This is more like the brain that a centralized computer. Understood? It is like a brain than a centralized computer. Technically, BDH uses local rule sets or nodes and edges to perform inferences, making it interpretable and biological plausible. Now, to make this efficient, they introduce BDH-GPU, where instead of explicit graph communications, neurons communicate through a mean field like a broadcast network, like a classroom announcement instead of one-to-one conversations. This reduces the complexity while keeping the same behavior. So BDH GPU has about 3 plus O of 1 in D parameters, where N is the number of neurons and D is approximately 256. And it still matches the transformer performance, which has 10 million to 1 billion parameters. Another key point is that activations are highly dimensional, positive and sparse, meaning only a few neurons are active at a time, just like the brain. The model also shows emergent graph structure and synapse level interpretability, meaning we can track reasoning at a level of individual connections. Overall, this work bridges transformer style attentions, macro level with neuron level interaction, that is micro level, combining particle based systems and logic reasoning into one unified network. Now, this figure shows how different AI architecture related to each other, especially how BDH and BDH GPU act as a bridge between transformers and brain like models. On the left, Transformers use centralized tensor operations like attentions via KV cache and feed-forward networks MLFs. On the right, brain model uses distributed graph dynamics where neurons interact locally through synaptic connections and plasticity. Now, the BDH lies fully in the graph-based world, while local neuron-to-neuron interactions and edge-based state, that's sigma. While BDH-GPU sits in between, it keeps transformer-like tensor computation, but internally represents state in neuron dimension n, and mimics mean field communication like broadcast instead of direct wiring. You can relate it like a transformer is a centralized computer and brain is a decentralized network, and BDH GPU is a hybrid systems that behave like both. The key idea is that attention and feed forward layers at macro level correspond to a local neuron interaction at micro level, making BDH a unifying framework. So in this section, the authors defines the mathematical language used in paper using state space models and graphs. The model is described using two things: parameter m, that's fixed, and state sigma t, that's dynamic. And it evolves over time using an equation like sigma t plus 1 equals to a of m sigma t at, where at is input like a token, and think of it like a game. M is the game rules, sigma t is the current game state, and every move updates the state step by step. They also explain that a model can be seen like a program, where M is the code and sigma is the memory, changing during the execution. Then they connect these two graphs where a matrix H implies to Rnn represents a network of n nodes, and each value h of ij is a connection, edge weight. This can be understood like this: imagine n cities connected by roads, and like h of ij tells how easy it is to travel from city I to city j. When we multiply h with the vector v, it spreads information across the network, similar to Markov chains where probabilities move between states. They also explain that combining two graphs h1 and h2 is like applying two steps of transitions h2 h1. Finally, they note that a sparse graph with m edges can be stored efficiently using about O of m parameters, which is important for scaling large models. Now, to formally define BDH as a distributed graph-based systems where computation happens locally on n neurons and communication happens through edges, that's synapses. The system runs in steps using a state space update rule and follows a synchronous scheduler with two phases: computation at each node and communication between connected nodes. Like imagine n people working in rounds. First they think individually, then they exchange messages with neighbors. The architecture uses four kernels, that's K1, K2, K3, K4, executed cyclically, that R is equals to I mod 4, which defines structured reasoning step. The core math comes from the interaction kernel, that is equation 3. Now, this equation means the new state of variable k depends on 1. Decay of its own value via decay, and 2. Contributors from pairs ij interaction with strength r ijk. Like I would say an example: if two ideas I and j come together, they generate a new idea k, and the more often they occur together, the stronger k becomes. This is simple to a chemical reaction or a population dynamics where quality evolves based on the interaction. Then they simply using binary 0-1 spiking signals where interaction like Qi and Qj behaves like AND gate, meaning both signals must be active. This is like neurons firing together. Now to make this work on graphs, they restrict interactions so that I and j are nodes and k is the edge or node connected to them, leading to the edge reweighting kernel where nodes store activations like x of I and edges store relationships and the state like z of ij. Now, this can be introduced like understood like instead of just updating people that are nodes, the system also updates the relationships as edges, making it more powerful than traditional models. Finally, they note that such systems have O of n nodes and m edges, where typically n is less than m less than n square, making them scalable and expressive for reasoning tasks. In this section, the authors defines how the BDH actually performs reasoning using graph dynamics, which they call equations of reasoning, as I state in the start. The system has n neurons and edges state sigma ij, acting like a memory, along with node variables that xi, yi, ei that represent activation signals. You can relate it like a stop. Imagine n people passing signals and their relationships change over time based on the interaction. The system runs in cycles of 4 L steps. For example, as L is 8 layers, it implies 32 rounds, where each round updates node, states, and communication across edges. The core idea is that reasoning happens through repeated updates of node and edge values. Even though the full equation are implemented locally in the table 1, they are mathematically equivalent to state space equation, that's equation 6, meaning the whole systems evolve step by step, like sigma t plus 1 is equals to a of m of sigma t. Each neurons updates its value like xi, yi, ei is fast signals like spikes. Sigma ij is a slower memory updates that are fast updates. I key operation is thresholding, which means a neuron only activates if excitation is greater than inhibition, similar to real neurons. Like if positive signals like a friend supporting an idea are stronger than negative signals that's critics, then the idea activates. Like as a normal human beings. Also, it states that sigma ij are maintained per layer, where L is 0 to L minus 1, which helps balance parameter count versus state size. And overall, the system has about O of n plus EGS state variables. Training involves learning graph weights like this equation. These weights are there. Finally, instead of explicitly storing large graphs, they later approximate these using lower ranked answers, representations in BDH-GPU for efficiency. So overall, this section shows that reasoning equals to local neuron updates plus edge memory updates over multiple rounds, forming a deep layered inference process similar to transformers but implemented as a graph system. Now, this table is basically showing the equations of reasoning, how the BDH model thinks step by step using neurons and connection like a brain. It works in cycle of 4 rounds, that's 4L to 4L plus 3, and each round does a specific job. Round 4-1, inference from state. The model uses current neuron, activates Xi and connection strengthens sigma ij to produce slightly activation, that's aj. Also, sigma slightly decays by 1 minus uij like a forgetting old information. Now, round 4L plus 1, learning and synapse update. Using yi and xj, the model updates connection strength, that's sigma ij, via gsij, and this is Hebbian learning. Neurons that fire together wire together. Now, round 4L plus 2, computation with parameters. You might be able to relate what I was saying in the earlier, and these table is signifying all these things. Now 4L plus 2 is signal flow using learned weights, that's gy, to update neuron states, that yj, combining excitation and inhibition using thresholded like ye minus yi plus, meaning only positive signals survive. Now round 4L plus 3, That's the final inference steps. Signal flow against using gx weights to update xj, completing one reasoning cycle. The bottom table B adds more details like split signals into excitatory E and inhibitory I paths, shows communication between neurons and computation inside the neurons separately using thresholding like xc minus xi plus is like a neurons firing only if input is strong enough. Now the intuition is simple. You can relate this like a group of people solving a problem. First, they share current ideas, that is round 1. Then, strengthen useful connection, that's round 2. Then, process ideas with logic, that's round 3. Then, update the final beliefs, that's round 4. And this repeats for layer L layers per token. Now, in BDH, attention is not just a matrix level like in a transformers, but a micro level rule stored in edges, which acts like a bias for reasoning. Basically, if neuron I activates with strength XTI and the past has learned a connection, then neuron J gets activated with strength. And you can relate that if you strongly believe A and you previously learned A implies B, then you naturally start believing B more. Technically, this is similar to modus ponens and resembles the logic rule. But instead of true false, it uses weighted probabilities. And the sigma ij is not truth but a probabilistic inductive biases guiding which reasoning path to follow next. You can relate this like navigating a city where stronger roads is higher sigma and more likely to be chosen. So chains of reasoning become paths in a graph of n neurons, and attention dynamically opens this path based on the context. This figure shows a physical analogy of the BDH model using a network of particles and connections. Nodes that are in circles are neurons, edges that are in lines are connection between neurons. Sigma ij is the elastic spring between neurons that stores the memory, that's the synaptic state. X and Y that are blue and red signals, these are fast activation pulses moving across the nodes. GX, GY, GS, these are the different types of connection graphs, wires, prods, and elastic links. Now, what's happening is like a system of balls connected by springs. When one node activates like a pulse X or Y, it sends a signal through connections GX or GY, and this changes the tension in spring, that's sigma, which slowly stores information over time. The core idea is fast signal is equals to computation, that's the reasoning step, and slow changing in sigma is the memory, learning from past interactions. If I would say BDH behaves like a dynamic physical systems where signals flow quickly between neurons while connections slowly adapt and store knowledge. Now the paper shows that BDH can actually be implemented using brain-like mechanism, meaning real neurons could theoretically perform the same reasoning. But technically, BDH uses n neurons and O of n square synaptic connections, where reasoning happens through 4-step cycle, round 4L to 4L plus 3, involving activation, learning, and signal propagation. Like how your brain learns if two neurons fire together, their combination and connection strengthened in Hebbian Learning. So next time the signal flows faster. Mathematically, in round 4L plus 1, the update rule behaves like sigma ij is equals to sigma ij plus xj dot yi. That's Hebbian and like update. In round 4 plus 2, neurons apply thresholding, meaning only strong signals survive, and round 4L signals propagate using excite dot sigma ij implies A of j, showing how memory sigma directly affects reasoning. Like if you repeatedly connect idea A to B, your brain quickly jumps from A to B later. Overall, this proves that simple biological rules are enough to achieve transformer level reasoning, meaning intelligence can emerge from local neuron interactions. Now, these are the key equations where sigma ij update learning implies increase with neurons co-activate and it behaves like sigma I is proportional to xj and yi. This is the Hebbian rules that fire together, wire together. Now, thresholding is neuron firing. You see ye minus yi plus is the output only if excitation is inhibition. Then comes the reasoning set that inference. Here xi dot sigma ij implies a of j. This is the memory guide next activations. Then comes the system scales. Neurons are n, connections of O on n square, and reasoning cycle is in 4L steps. Now, the author convert the BDH model into a GPU friendly tensor model, that's BDH-GPU. So it can be trained like a model deep learning system such as transformers. Instead of explicitly stores huge graph of size n cross n, which is too expensive when n is large, example n is equals to millions approximately, they compress interaction using low rank representations of dynamic dimension d. Like d is equals to 256 where d is less than n. Meaning each neuron stores only a small vector instead of full connections. You can relate instead of every student in a school remembering every other student implies O of n square memory, and each student keeps a short summary vector of size d, and interaction happen through these summaries using linear attention, which approximate the full communication efficiency. So the model uses ReLU. You know ReLU? ReLU is Z plus, which equals to max of 0 and Z. To keep these activations positive and sparse, layer and layer norm to stabilize training by normalizing mean and variance. Technically, encoder matrices E is subset of uh, R power D cross N. That's compress high dimensional neuron states that Z to Z star and decoder matrix that D subset of R power N cross D. Then expand them back. So computation happens in low dimension but still represents a large system. The key idea is BDH-GPU simulates graph-based reasoning using tensor operations, making it scalable and trainable with backpropagation like GPT models. BDH-GPU is formally defined as state space systems, meaning the model updates its internal state step by step over time t and layers using equations. Imagine each neuron is a student, updating their knowledge in every round. First, they receive information, that's attention, then process it with non-linearity and normalizations, and then store it for further steps. The first equation means the neuron updates its current state by adding new information passed through a decoder matrix, that's D cross size n cross t, and a ReLU which keeps only positive signal, like ignoring weak or negative signals, which we usually don't do in life. As you can see, life lessons also in between. The second equation is defined attention. That's which means the model looks at all the past states and then combine them using a linear attention mechanism where it controls how past information decays or rotates, like memory fading over time. You don't know what you have done in when you were small, but you are not forgetting all the things, you are just fading a memory. Then this equation means the model processes this attention using another decoder, that's dy, and applies layer norm, that's stabilizations and ReLU, and multiplies its element wise with current state. This acts like gating or filtering important signals. Finally, it compresses the high dimensional neuron state of size n into low dimensional vector of size t using encoder. which is then reused in next step. The attention state summarizes all the past interactions compactly. Overall, the system behaves like a transformer but with linear attention and compressed memory, scaling as O of nd instead of n squared. Now, in this section, the paper explains that BDH-GPU can be viewed as a system of n interacting particles that are neurons, where each particle stores a small internal memory vector and communicates with other particles using low dimensional messages instead of huge matrices. You can relate this like imagine a crowd of millions of people that are n particles, where each person carries a short profile card like of size D, that's 256 we have like fixed it. So instead of remembering everything about everyone else, each particle has four important components: its current memory, uh, three trainable vectors, that's EI, TX and DY, that controls how it sends and receives informations. The equation means the particle state is collected across all layers, while it defines the full identity of one particle. The model uses mean field interaction, meaning particles do not talk one to one directly. Instead, every particle broadcasts a message. All messages are summed into a global signal, and every particle updates itself using this shared field. Now, this is similar to how radio broadcasting works. One global signal reaches everyone at once. Technically, this reduces communication complexity and allows the system to scale efficiently in dimension n, while every transformer still passes through low rank dimension d, making the model GPU efficient. Let's explain these equations. Now, particle state equations. This means particle I stores a memory vector for every layer L. If there are 8 layers, then one particle keeping 8 small memory vectors. Like this acts like a short-term memory of a neuron during the inference. Now the particle entity tuple. This defines everything about one particle. Here PIT is the current context memory, EI is the encoder behavior, DX is how particle receives X signals, DY is how particle receives Y signals. You can think of it like a social media profile. Memory, history, how the person listens and how they respond. Now mean field broadcast equations. Here every particle sends a message MJ and the system combines them into one shared global message. Like instead of millions of pairwise conversations, everyone hears one global broadcast signals. Now, it explains that BDH GPU and BDH are mathematically equivalent systems, meaning both models perform the same reasoning process even though one is tensor based, that's GPU friendly, and the other is graph based, that's brain like. You can relate this like imagine two navigation systems are there. One stores roads as a huge matrix on the computer while the other stores them as a connected street in a city map. Even though the storage method is different, but both still guide cars to the same destination. The paper shows that this equivalence using equation 9 here d of ed underscore this and d of yed convert tensor operation of BDH GPU into graph communication rules in BDH. The matrix means every neuron can potentially connect to every other neuron, creating a full connected attention graph. The important idea is that both systems use only O of ND parameters instead of huge n square storage, where n is the number of neurons and D is the lower rank dimension. The paper further explains the BDH can represent these large neuron interaction matrices using sparse graph through a hidden synaptic layer S, which acts like immediate relay station. Like instead of every city having direct flights to every other city, which will be n square routes, a few hub airports reduces the total number of connections while still allowing communication between all cities efficiently. Now, this core equivalence equation, this means D underscore X decoder, it is a decoder matrix, E is the encoder matrix, and their multiplication creates the same communication behavior as the graph connection in BDH. Now, the second equivalence is having the same idea but for the Y signal pathway. It's for excitatory and inhibitory graphs dynamics in BDH that can reproduce the same transformers as tensor operations in BDH-GPU. Now the attention graph equation. This means every neuron is connected to every other neuron. So the total possible synapses would be n square. Now the sparse graph class. This means a graph G can be represented as the square of another sparse graph H where H has m edges. Like instead of storing all connection directly, the model stores compact relay connections. Now the graph-based propagation equation. This represents important information propagation through the neuron graph. Now the sparse propagation replacement. This means instead of one huge dense graph, do two smaller sparse graphs process. This dramatically reduces memory and computation. Like you can relate this, imagine WhatsApp communication between 1 million users. A fully connected system needs every user connected to everyone else. That's n square connections. So BDH instead create group hubs or relay servers that message travel through hubs in two steps but still reach everyone efficiently. That is exactly what the sparse graph H does. This figure 5 explains how BDH converts a large dense neuron connection graph into a small sparse communication systems using an intermediate hidden layer. You can relate this like imagine every student in a school directly messaging every other student. That would need huge connection, that's n square as usual. Instead, messaging first go through a few class representatives or hubs, making communication efficient while still allowing information to reach everyone. On the left side, the graph is shown, which is H, where V is neuron nodes, S is hidden sparse synaptic layer, and the neurons communicate indirectly through immediate nodes. For example, these two paths together creates the effective connection, and this means the final neuron-neuron interaction strengthened between neurons I and J is built by combining multiple shorter sparse paths. On the right side, the paper shows the final interaction graph, which means instead of storing all the direct neurons connections, the system computes them using two-hop communication through sparse and immediate nodes. This reduces the memory and parameters from huge dense storage to efficient smart sparse propagation while preserving the reasoning ability. Now, this section explains how BDH GPU scales efficiently like transformers while using a brain inspired neuron systems. And like imagine a school where instead of every student remembering the whole textbook, each student stores only a small specialized parts of the information, and together the school solves a complex problem. Now, BDH GPU mainly scales with the neuron dimension n, while D is much smaller compressed, that's synaptic memory. Dimension where D is less than n of T and ND is less than n. The total parameters are 3 plus O of when ND model size, which grows linearly, not quadratically, because the model mainly stores three matrices, each of sign n cross D. For example, if we have 25 million parameter model and D is equals to 6, n is equals to 32768, huge neuron count with compact neuron memory, meaning the system has 32,768 neurons, as each neuron stores 3D, that's 3 into 256, which is 7638D. Yeah, so it has this much of parameters, and the model uses linear attention instead of quadratic transform attentions, and its state is n cross t for every layer, and acting like a large associated memory similar to KV cache, but permanently aligned with the neurons. Unlike transformers, BDH GPU has no fixed context window, meaning it can theoretically remember infinitely long sequences. The attention vector xt is constrained to positive values using ReLU, and becomes naturally sparse during training, where only about p is 5%, rho is 5% of neurons activate for a token. Like when you hear the word football, you can relate it like this. When you hear a word football, only a small subset of our brain neurons related to that sport become active, not your entire brain. So the computation cost during inference is O of NDL, where N is the neurons, D is synaptic dimension, and L is layers. This is important because transformer attention usually scale quadratically with context length, but BDH GPU scales linearly and remains efficient for very long context, like greater than 4096 tokens. The paper also experimentally shows BDH GPU follows transformer like scaling laws and often learns faster per token than GPT style transformers, especially while training data is limited. Now, this figure shows a complete layer of BDH GPU architecture and how information flows through the model during reasoning. Like, imagine a brain inspired system where neurons first compress information into a small memory space, reason over it using attention, and then expand back to activate important neurons. The left side starts with previous activations and XL minus 1 and YL minus 1, which passes through the encoder matrix to compress large neurons activation of size n into a smaller synaptic representation of size t. This compressed vector is V star V, which acts like a combined key value representation. Then the model updates the attention memory using PL plus equals to XITV. This is called rank 1 key value update, meaning every token slightly modifies the model's long-term associate memory. When you hear a new sentence, your brain slightly strengthens association between related concepts. The attention block then uses this stored memory with a query to retrieve relevant information from linear attention instead of expensive quadratic transformer attention. The retrieved information passes through decoder matrix, that's dx and dy, which expands the compressed d-dimensional information back into the large neuron space n. ReLU activates keeps only positive and important neuron activations, making the activation sparse. The state matrix persists over time, meaning the model continuously remembers past information without a fixed context window. Now, this section explains how BDH GPU compares with other AI sequences models like transformers. Linear attention models, reformer, spark transformer, and oscillatory state space models. The main idea is that the BDH GPU combines the best property of many existing architecture into one unified systems. Like transformers are very fast sport cars for short distances. SSMs are fuel efficient long distance vehicles, and BDH GPU tries to combine both speed and memory efficiency together. The paper says BDH GPU performs linear attention in a very large neuron space instead of compressing attention into smaller dimension, which helps preserve more information during reasoning. For example, in figure 7, BDH GPU rescales mainly by increasing the number of neurons n, while GPT models must increase both embedding size and layer, making scaling harder. The paper also explains that BDH-GPU naturally creates sparse activations where only 5 to 8% neurons become active, similar to how a fewer brain neurons fire for a specific thought. Another important point is that BDH-GPU has no fixed context window, unlike transformers that forget information after a limit like 8K or 4K tokens. Like, it is a student who keeps updating long term memory instead of rereading only the last few pages before answering. The section also connects BDH GPU to oscillatory systems, meaning it says its state behaves like waves or rhythmic signals, similar to brain activity or vibrating springs discussed earlier in the second sections. Overall, the author argues that BDH-GP unifies ideas from linear attention, sparse activations, recurrent memory, LSH attention, and oscillatory SSMs into one biologically inspired reasoning architecture. Let's take an example. In a normal transformers, if the context window is 4096 tokens, the models mainly focus on recent informations. But BDH GPU works more like a continuous updating memory system where only a few important neurons activate and store useful information over long durations. Like, this is how humans remembers only important parts of a longer conversation instead of every single word. Now, this section explains how one of the most important ideas of the paper, that's BDH GPU, naturally develops modular and scale free structure during training instead of engineers manually designing modules. Like how social networks on the human brain organize themselves into communities automatically. For example, in a school, student interested in sports, coding, or music naturally forms groups, but some students connect with multiple groups together. Similarly, BDH neurons forms communities that specialize in certain topics while still sharing information globally. The paper explained that this modular structure improves both efficient transformation, propagation, and reasoning accuracy. A very important concept here is that scale free property, where a few neurons becomes highly connected hub neurons while many others have fewer connections. Similar to how Google or Wikipedia pages receive many more links than normal pages. This creates stable yet adaptable reasoning behavior. The section also introduces the ReLU low rank proc, where signals are compressed from a huge neuron space N into smaller hidden dimension D, then expand back again using matrices E, dx, dy. Like, you can understand, compressing a large image into a zip file and reconstructing it efficiently while keeping important patterns. Let's take an example. Suppose the model has 32,768 neurons, but compresses signals into only 268 hidden features before rebuilding them. This helps the system keeps important information while removing noise and reducing computations. It means first apply matrix multiplications, then apply ReLU, so only positive activation survives. This makes activation sparse and reduces noises. Now, the paper compares this to transformer MLP layers and argues that BDH GPU can still approximate complex functions while using a biologically inspired sparse positive activation systems. Another important point is that BDH GPU only works in the positive quadrant, meaning neurons' activations stay non-negative, similar to real neurons firing strength in biology. Why then ReLU low rank block works as a smart signal propagation system instead of just a complex matrix multiplication? Why? So you can relate this like, imagine a huge social network with uh, 1 lakh, more than 1 lakh, 10 lakh people, but instead of storing every possible connection between all people, the model compresses interactions into a much smaller hidden space like size t. The paper says that a normal low rank approximation, that G is equal to DE, can approximately preserve pairwise relations between node wise. but it introduces noises. The important equations here is this means that as the hidden dimension d increases, the approximation error decreases roughly proportional to log of n. But the paper explains that linear low rank alone is not enough because errors become large in global vector transformation. That is why they introduces the ReLU low rank operation. Here the ReLU removes negative noisy activations and keeps only meaningful positive signals. If a neuron should send signal only to 5 important neurons out of 10,000, the low rank multiplications may accidentally activate hundreds of noisy neurons slightly, but ReLU acts like a filter threshold and suppresses weak noise value to 0. The paper then proves and claims that even sparse graph propagation like a random walk with degree r can be approximated efficiently using d is equals to O of r cube log n by epsilon. Thus are the hidden dimensions. This is important because it shows BDH-GPU. It can simulate graph-based reasoning without storing huge dense matrices. The core idea is low rank gives compression, ReLU gives noise filtering, and together they create stable signal propagation in very high dimensional neuron space. Now, this section explains how BDH-GPU naturally creates modular communities of neurons that selectively activate together. Similar to how groups of friends in a social network respond more strongly to messages inside their own group. Like, imagine a school where students are divided into clubs like robotics, music, and sports. If a robotics related message spreads, mostly robotic students react because they share many internal connections. In BDH GPU neurons behave similarly using the ReLU low rank mechanism. The important equation is equation 12. Here, Wj is the activation strength of neuron J over Varro means which measures how much overlap exists between the currently active hidden neurons A and the neurons connected to neuron J called Pj. In simple terms, larger overlap Cj equals to A means neuron J is more likely to activate. Let's take an example. Suppose A contains 100 active hidden neurons related to translations, and neuron J1 shares 80 of those connections, while neuron J2 shares only 5. Then J1 strongly activates but J2 does not, exactly like shown in figure 8. The figure 8 explains this visually. On the left, signal travel through the sparse hidden synaptic layer, and on the right, neuron J1 receives enough overlapping community signals to cross the ReLU threshold, while neuron J2 fails. The paper connects this to modular graph theory using stochastic block models (SBM), where neurons inside the same cluster communicate more efficiently. The important insight is that BDH-GPU does not manually create modules. Modular neuron communicates emerge automatically through signal reinforcement and thresholding. The paper also introduces supermodularity, meaning combining two weak signals together can suddenly activate a strong response, similar to how partial clues together suddenly help you solve a puzzle. Mean selective equations here is this: A is currently active hidden neurons and Bj is the hidden neurons connected to neuron J, and Cj is equals to A cap Bj is overlap between them. If overlap is large, neuron J activates strongly. If overlap is small, ReLU suppresses the signal to 0. This is the mathematical reason why modular neurons communities emerge naturally in BDH and CPU. Now after training, the matrices inside BDH-GPU automatically organizes themselves in modular graph structures, meaning group of neurons start forming communities that communicate more strongly with each other. You can relate this like a structural network with similar interest of group I just said. Here the matrix multiplication operation, which means the input signal Z first passes through the low rank matrix T and E, and then ReLU keeps only positive activations. acting like a filter that removes weak noisy signals. The paper said the learned graph G equals to DE develops at heavy trained distributions, meaning a few neuron connections becomes extremely strong while most stay weak. Similar to how a few influencers in social media have a huge reach while most users have small influence. Equation 30 is the key equation because it breaks the learned matrix into four parts: true positive, signal inhibitory, negative signal, Gaussian noise from low rank approximations, and trainable bias correction. Here, B in simple words, the model learns useful neuron relationships while also handling random noise mathematically. Now, figure 9a shows that the right side of the distribution have a long heavy tail, meaning some neuron connections are much stronger than others. And figure 9b shows strong connections form highly modular communities unlike random graphs. Figure 10 further shows a powerful law degree distributions, meaning a few neurons becomes highly connected hub neurons, creating a scale-free network similar to the internet or brain networks. The important result is empirical finding 3, where the paper confirms that modular graph structure naturally emerge during training because they help efficient information propagations. Now, this section explains how the linear attention mechanism in BDH-GPU works efficiently even without transformer-style software attentions. Like it's a giant smart library system where every book is a key is stored with its meaning, that's value. And when a question that's query comes, the system quickly finds related books using similarity between key and the queries. In BDH GPU, the key query vectors live in a very large neuron space, that's RN, instead of a smaller transformer embedding space, and importantly, all activations are positive sparse vectors. The core attention equation is this, where KT is the current query, KT are previous keys, VT are stored values, and phi measures similarity between them. The paper explains that if a neuron dimension is very large, linear attention can distinguish up to approximately um, till D of n. Facts and memory, which means more neurons directly increase memory capacity. You can relate this like having 1,000 of labeled drawers in a warehouse. The more the drawers you have, the more unique items you can separate without confusion. Equation 5 explains how BDH GPU converts concepts into positive sparse vectors using LSH style bucket activations, meaning each neuron acts like a bucket detector, deciding whether some features exist or not. Observation 8 is the very important because it shows BDH GPU can strong separate even slightly different concepts using dot product attention. The example with vectors x1 and x2 shows that two vectors can look almost identical in probability terms but still produce very different tension scores, helping the model distinguish subtle meaning in language. The section also explains why BDH GPU naturally supports long context lengths. Unlike transformers, it has no fixed context window, and higher layers gradually denoise irrelevant information. So, only important memories stay active over time. Now, how a BDH GPU attention works at two levels: a macro level, that's overall attention mechanism, and the micro level, that's individual neuron to neuron connections called synapses. You can relate it like a huge social networks where neurons continuously create a strengthened relationships based on the concept they frequently see together. Like the robotics thing, the paper reconstruct a neuron connection matrix called sigma using equation 16. And why are neurons activations, and the equation basically stores how strongly neurons influence each other over time, while ut tau adds positional memory, like it's a brain remembering that certain words or concept repeatedly appear together. Figure 11 is then important because it shows a neuron graph follows a scale free and power law structure. meaning a few neurons become highly concentrated and becomes hub neurons, while most have fewer links, similar to how a few famous websites or influencers get most connections on the internet. The paper then finds monosemantic synapses, meaning some neurons connections activate only for one concept, like currency or country names. For example, the same synapses activates for both British pounds and lire sterling, showing the model understands semantic meaning, not just exact words. Now, this figure 12 highlights the selective activation behavior. The paper statistically validates this using the Mann-Whitney U test, where U is 2368 out of 2500 and P is less than 10 to 14, proving the synapse strongly correlates and currency related sentences. Finally, figure 14 explains sparse activations. When input becomes predictable, higher layer neurons becomes more inactive to save computation and energy. Like, students become silent once they fully understand the repeated patterns. This means BDH activates neurons mainly for surprising or important information, similar to adaptive computations in a human brain, improving efficiency, interpretability, and long context memory. Now, this figure 12 shows monosemantic synapses in BDH-GPU, meaning specific neuron connections activate only for one semantic concept, like currencies or countries. You can relate like this is a brain neuron that reacts only when it hears money related words. Here, whenever words like yen, dollar, euro, rupees appear, the currency synapse value sharply increases. Similarly, country-related words activate the country synapse. The important point is that the same synapse activate across multiple languages like English, French, Spanish, and Portuguese. For example, both British pound and lire sterling trigger the same neuron connections. This proves the model learning semantic meaning, not memorizing exact words. This directly connects to the earlier discussion of sparse activation and modularity, where only 1,000 specialized neurons become active for important concept, improving the interpretability and reducing the noise in attention. Now this figure 13 and 14 together explain how BDH-GPU use sparse neuron activations to build meaningful memory connections. Like a human brain, something important or surprising happens. In figure 13, when the sentence contains the concept US dollar, only a few neurons YI and XJ activate, and this strengthens the synapse between them using a Hebbian learning rules, like neurons that wire together. This creates a specialized currency synapse, which connects directly to the monosemantic behavior discussed earlier. And then figure 14 shows that once the model has memorized a repeated pattern, neuron activity becomes very low and sparse, especially in higher layers. Like a student becomes quiet once they understand already they know the answer. During memorizations, layer 2 activity rises to around 4 to 7.5%, but during repetition, it drops to around 2.5%, proving the model activates neurons mainly for new information and stays energy efficient for predictable inputs. This supports adaptive computation, lower noise in attention memory, and better interpretability. Now, this section explains the BDH GPU models can be merged almost like combining Lego blocks. Basically, because the architecture mainly scales by increasing the neuron dimension n, like it's like two students learning different languages separately and then combining their notebooks into one bigger notebook. First, the researchers trained a 19 million parameter model with n equals to 2550 576 on English and Spanish, then separately fine-tuned copies on English French and English Portuguese. After that, they directly merged both models by concatenating neuron-related matrices like DX, DY, E along the neuron dimension, doubling the neurons to 4900 and 192, and creating 49,152 actually, and creating a 38 million parameter model. While any retreating, The surprising result in Table 2 and Figure 15 is that the merged model could still translate French, Spanish, and Portuguese into English, but when translating from English, it mixed all three languages together. You can understand this like a person who understands multiple languages while listening, but while speaking mixes grammar and vocabulary from all of them. This behavior supports the earlier idea of monosemantic and distangled concept representations, where concepts are stored in separable neuron groups, making direct composition possible. Figure 15 visually shows this language mixing effect, while also proving that model preserved semantic meaning even after meaning merging. The second part explains training without backpropagation through time, that BPTG. Normally, transformers send gradient across long sentences, but BDH Sparse synapse updates allow approximately learning without storing the whole history. However, performance drops. English loss increase about 0.65 to 0.75 to 1.05, and the model loss strong translations alignment between languages. This shows temporal memory learning is still important, even though sparse activities reduces computation and memory cost. Now, this conclusion section says that BDH-GPU is designed more like a brain-inspired and scalable AI system where everything works in one large neuron space of size n instead of many disconnected modules like transformers. You can relate it to like a huge city I had already had all the tools and information nearby, so less time is wasted moving data around. The paper says that this reduces the major bottleneck called memory to core bandwidth. The authors also explain that because of the model has sparse neuron activations that only a few neurons activate at a time, it becomes easier to inspect, debug, merge, and even directly modify models, almost like combining computer programs. For example, earlier they merged two languages models simply by concatenating neuron dimensions, showing that concept can be combined directly. In figure 13-14, sparse activations and synapse update supports this idea, and only important neuron connections becomes active, which improves explainability and efficiency. The paper also connects this to neuroscience, saying attention and reasoning in the brain may emerge from local neuron to neuron communication and Hebbian style edge reweighting instead of mysterious global learning processes. A very important equation like idea here is the sparsity relation. That's 1 by rho is approximately 22 ones, meaning if only about 5% of neurons are active, a synapse charge changes rarely, making memory and gradient flow simpler and more efficient. The authors finally argue that understanding these local reasoning dynamics could help build safer, more controllable AI systems in the future. Okay, now let me give you a full paper in just 5 minutes. The big picture, the core ideas, and why it actually matters. So, the problem is right now AI models like ChatGPT are powerful, but they have one big weakness. They can't truly reason over long periods of time, the way your brain does. If you give a transformer a task longer than what it saw during training, it starts to fail. And nobody fully understands why. Because current AI is built like a centralized computer, while your brain is distributed networks of 80 billion neurons all talking locally. These two worlds have never been properly connected until now. And the big idea is the author of this paper from a company called Pathway introduces a new architecture called BDH, a strong short for Dragon Hatchling. The core idea is this: what if we build a language model that actually looks like a brain at the mathematical level? Not as a metaphor, but formally, as a graph of neurons connected by synapses, where reasoning happens through local interaction just like biology. They uses two classic ideas. First, modus ponens, that's a basic logic. If A implies B and you know B, you conclude B. Second is Hebbian learning. Neurons that fire together wire together. The model reasons using logic and strengthens its own connection as it thinks. That's the core magic. Now, the architecture. A pure brain graph model wouldn't run on a GPU. So the authors do something clever. They create BDH-GPU, a version that keeps all the brain-like mathematical properties but runs efficiently as tensor operations just like a transformer. Here's how it scales. The model has n neurons which can be tens of thousands or millions, and each neuron stored a tiny compressed vector of size t, where d is around 256. So the total parameters is just a 3 times n times t. That's it. Compare this to a transformer which needs separate weight matrix for key, queries, values, MLPs. BDH GPU does it all with three matrices, that's E, dx, and dy. Instead of expensive quadratic attention, BDH GPU uses linear attention in a very large space, so it has no context window limit. It can theoretically remember forever. And what's surprising here is where it gets really interesting. After training, the models spontaneously develops properties that look exactly like a brain without being programmed to. First is sparse activations. Only about 5% of the neuron fire for any given token, just like real neurons. Your brain doesn't light up all at once, neither does BDH. Second, monosemantic synapses. The paper shows that specific neurons connections become dedicated to specific concept. There's literally a currency synapse that activates whenever it sees yen, dollar, rupees in English, French, Spanish, and Portuguese. Same synapse, different languages. Third, that's scale-free graph structure. A few hub neurons become highly connected while most stay sparsely connected, exactly like the internet or your brain. None of this was forced. It emerged naturally from the architecture. So, does it actually work? Yes, the paper shows BDH GPU matches GPT-2 transformer performance at every scale from 10 billion to 1 billion parameters on languages and translation tasks, and it often learns faster per token, meaning it needs less data to reach the same quality. They also showed you can merge two BDH models by literally concatenating their neurons matrices, like stacking a Lego block, and the combined model inherits knowledge from both, no retraining needed. So, what does this all mean? The author argued this in the first mathematical bridge between transformer style AI and the actual brain. The equation that BDH uses to reason, they call them the equations of reasoning, turns out to be equivalent to what spiking neurons and the Hebbian synapse do in your head when you think. This matter beyond performance. If we understand how a model reasons at the neural level, we can inspect it, control it, predict how it will behave over long time scales, and build what the author called axiomatic AI. AI where the micro level rules and the macro level behavior are both understood and consistent. So, in one line, BDH is a language model that thinks like a brain, runs like a transformer, explains itself like a textbook, and scale like a clean mathematical systems. It connects two worlds, artificial intelligence and neuroscience through a single unified framework. This is Dragon Hatchling, and if you want a full breakdown, every equations, every figure, every experiment explained with examples, that's what the entire video has been. But now you have got the map and you can look it into it. Thank you.